Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good morning. So this week we will start our online class session with chapter 2 about performance parameters of jet engines. Okay. Okay, so last week I have introduced to you, I've explained a bit about the introduction to aircraft propulsion. Okay, so we have seen several types of aircraft engine, which is turbojet, turbofan, turboprop, ramjet, etc. Right? And we will see. We have seen the applications, power plant, aerospace applications. Right? Okay. So this week, this next chapter, we are going. I'm going to introduce to you the performance parameters that we have to know in order to calculate, to solve, to design, even to aerospace propulsion. Okay, so so this week in this session, this chapter, I will introduce to you first those parameters, and next week, inshallah, we will see some tutorials, exercise to do. Okay, some examples. Okay, inshallah. So this chapter will not be too long, just small chapter. Okay. As you've seen last week, right? I've asked you to try to derive by your own self the thrust force. Okay. So as I've explained, if we consider we have like the aircraft engine. Okay. Here, the aircraft engine, normally the turbofan engine. The aircraft engine here is like, we consider it as a closed system. Okay, so we try to derive the thrust force equation according, okay, for this closed system. Okay, so we start with the conservation by application of the conservation of momentum. Okay, the second conservation law of conservation. Okay, the conservation of momentum, which actually involves the Newton's second law, right? Newton's second law, the sum of the force equals to ma, or the sum of the force equals to mass flow rate times velocity. Okay, either one. So by knowing, okay, the theory, the fundamental that the sum of the force equals to ma, or m dot mass flow rate v, okay, multiplied with velocity, we use that definition and apply it to this closed system. Okay, so we know this closed system have input or initial parameter, V naught, A area, mass flow rate naught, which is usually the air, the mass flow rate of the air, and the pressure of the ambient, P naught. Okay, and at the exit, at the exhaust exit of the closed system engine, we have the velocity, the exhaust velocity or exit velocity. We have the mass flow rate, exit mass flow rate, which is expected to be the exit mass flow rate is the mix of the missing mass of air and fuel. Okay, because we are going to add some fuel in the middle of this engine within the combustion chamber, right? So within the combustion chamber, we are going to add fuel, and the fuel will mix up. Okay, will mix with air. Okay, air intake at the inlet, and will explode. Okay, so will combustion process will occur, and at the exit you will have the exit mass flow rate, which is not equal to the initial mass flow rate. So now at the exit we have not just air mass flow rate initially, but we also have the mass flow rate from the fuel. Okay, and then the exit pressure, okay, PE, and the exit area. Okay, okay, for this PE, okay, we will look at it later on. Okay, PE, exit pressure, sometimes it is equals to, which is in ideal case, it is equals to P naught, P initial, which is the ambient pressure. Okay, so we assume that PE, exit pressure, is equal to P naught, which is the ambient pressure, environment pressure. Okay, or sometimes the PE is higher or lower than the ambient pressure. Okay, so there are different case studies. Okay, so by applying the Newton's second law, so we know that thrust is a force. Thrust is a type of force. Okay, so it is in Newton or kilogram per meter per second square. Okay, so we have the Newton's second law equation, but here we use the velocity, so we have to times multiply with mass flow rate, mass flow rate inlet and outlet, and plus, okay, so we call it, we define it, this term, okay, this term, both of this term, the first and second term, as the momentum force. Momentum force. Okay, so we define this part as momentum force. Plus, this part is what we call momentum thrust, because this is thrust force. Okay, momentum thrust, and this part is the pressure thrust. Okay, thrust that means that thrust that produce due to pressure, the difference of pressure. Okay, so PE, the exit, minus the difference to the P naught. Okay, equals to area. So here actually we consider that the area AE and A naught is equal. Otherwise, we have to multiply PE AE minus PO P naught A naught. Okay, if the area, exit, and inlet is different. Okay, so this term is pressure thrust. So what if, okay, in the ideal case or in the assumption that we made, sometimes we consider that the PE is equals to P naught, which is equals to ambient pressure, environment pressure. So we don't have this pressure thrust term anymore. Okay, so we cut out. Okay, this term is negligible, so we cut out this pressure thrust, so we only have the momentum thrust. Okay, this one. Okay, so mass flow rate times with velocity, exit, inlet. Okay, so as I've mentioned also just now, for when you apply conservation of momentum, you also need to know so the conservation of momentum is the second law, right? So that's why we need to know first we need to acknowledge first the first law of conservation, which is conservation of mass, or we call it as continuity equation. Okay, so when we solve this conservation of momentum, okay, we need to also apply that we acknowledge that the concept for conservation of mass means that the exit mass must be equal to the initial mass. Okay, so by knowing the conservation of mass, okay, so we know that mass inlet, okay, we have the mass naught, which is the air, the mass flow rate of the air intake, and m naught multiplied with F is actually the fuel, mass flow rate of the fuel. Okay, so actually you write the mass flow rate of the fuel in terms of mass flow rate of air. F, this notation F, okay, F is a ratio of fuel mass flow rate, MF, we write it as MF, fuel mass flow rate over the mass flow rate of air at the intake, M naught. Okay, so MF over M naught, or M initial, or M air. So that is what we call F. Okay, so I repeat it again. F is what we call fuel ratio. Okay, so it is a ratio of mass flow rate of the fuel over the mass flow rate of the air at the intake, or M naught, the initial. Okay, so that's how we got here this term. Okay, so it's actually M naught, which is initial value of the mass flow of the air, plus the fuel mass flow rate. Okay, fuel mass flow rate is defined by using F times the initial mass flow rate. Okay, so and then we introduce also another performance parameter, which is what we call specific thrust. Okay, specific thrust. Specific thrust is the ratio of the thrust force over the mass flow rate of the air intake. Okay, so actually this force equation uh, is divided by m naught, or m air at the intake. So we have this one, and replace this me with this one. Okay, so specific thrust, the second parameter. Specific thrust is what we call we are going to calculate how much the thrust produced, the thrust force produced with uh, uh, by a unit of air mass flow rate. Means that if we have 1 kilogram per second air mass flow rate at the intake, how much thrust force that we can produce? How much? Okay, so that is specific thrust. 1 kilogram of air mass flow rate equals to how much that we can produce thrust force. Okay, thrust force that we can produce. Okay, so next, so clear, we already have two parameters here. So and sometimes we use thrust force. Okay, we write it as T thrust. Okay, T thrust. Okay, I usually write it as T thrust, not F. Otherwise, I will get confused a bit. Okay, thrust with the general term for force. So I will write T thrust. Okay. Okay, so some other parameters equation, which is non-dimensional thrust equation, means that we can also rewrite, reform the thrust equation just now in terms of in non-dimensional equation, means that no unit. Okay. So look at here, okay? So the first equation here is the thrust force equation just now. So U is the velocity. So we have the mass force. Okay, excuse for this because when I transfer from the equation to PowerPoint, it didn't detect. Okay, so this is actually mass flow rate. Okay, so we have the same thrust equation here. Okay, resulting from the control volume just now. Okay, closed system here. Okay, so if we assume, or if we know that PE is equal to PA, means the exit pressure is equal to the ambient pressure. So this pressure thrust is negligible. So we only have this part. Okay, like just now I've mentioned. Okay, this one. Except that here we assume that the ME, it's not that we assume ME equals to M initial. It's just that usually, okay, this term, usually F, the fuel air ratio, usually is very, very small. Means that the fuel mass flow rate usually very small compared to the air mass flow rate, compared to the air mass flow rate. So sometimes, sorry, okay, so sometimes F is like 0.01 or 0.02 or 0 point something, right? So this term is approach to close to being negligible. Okay, so we can neglect this term sometimes to simplify. Okay, even though it is not the exact value, but to simplify it, because we know that fuel ratio will be very, very small compared to mass flow rate, air mass flow rate. So we neglect this term. So that's why we get only ME equals to MO or MA, mass flow rate. So means that we assume that the mass flow rate is the same. So that's why it can this equation we can factorize the mass flow rate. Okay, we assume that the fuel to air ratio or the fuel mass is very very small. It's not that it is null, is zero. It's just that it is very small. Okay. Okay, so this is the specific thrust. So we divide the thrust force by the mass flow rate. Okay, just now, and we factorize the initial or the air speed. Okay, or the aircraft speed here, the initial aircraft speed. Okay, U not here. Okay, we factorize it and we get this equation because we want to introduce to substitute, okay, the Mach number. Okay, so we know that the Mach number is a non-dimensional number, non-dimensional value, which is no unit. So the Mach number is the velocity of the fluid of the air over the acceleration speed of sound. Okay, and the speed of sound A, or sometimes we call it as C, is the square root of gamma. Okay, the constant value R and T. Okay. Okay, this one you already know in aerodynamic. Okay. So to introduce the Mach number, that's why we factorize like this. Okay. So finally, we have a non-dimensional term. Okay, which is for specific thrust. Okay, non-dimensional term for specific thrust. Okay, this is the real term for specific thrust. But if we want to reformulate the specific thrust in terms of non-dimensional, so we introduce the Mach number here. Okay, means that okay, we have UO just now, so UO equals to M naught times A naught, and A naught is divided, go to the left. Okay. Okay, so we have that equation, and then what else do we have here? Kind of the same thing, just to show you that how do we expand this non-dimensional equation with the exit velocity as well, with the exit at the exit. Okay, so we introduce also the Mach number at the exit in this equation. Okay, so UE is the velocity, so the Mach number times the speed of sound at the exit. Okay, so we have this one, so we substitute with this gamma RT, etc. So we only have this value. So it means that we can also find out, calculate the specific thrust if we only know the temperature. The Mach number means that we can use this correlation, this equation, if we don't have the value of velocity, but we want to calculate the specific thrust or the thrust, we can use this term, because this term you only need to know the Mach number. Okay, no need to know the velocity U or V. Okay, we only need the parameter for Mach number and temperature, and then we can find the thrust or specific thrust. Okay, like just now. Okay, this one you still need the velocity. This one you don't need the velocity, so you can use this if you don't have the information on the velocity. Okay, factors affecting thrust. So we have also to know which factors that affect the increment or decreasing thrust. Okay, so first one we have the nozzle. Okay, the jet nozzle. Okay, how do we design the nozzle in order to get thrust, pressure, temperature higher or below, right? Okay, or small. Okay. Okay, so normally we have two types of nozzle. Okay, so choke or unchoke. Okay, we use the term choke or unchoke here. Okay, choke or unchoke means that actually it's not like a choke, something like that. Tercekik tu kan. Okay, choke here means that it is limited. Okay, the fluid is limited. When you read choke nozzle or unchoked nozzle means that limited nozzle or unlimited nozzle means the air that is limited air nozzle or unlimited air nozzle. Okay, read it as in your mind, limited. Okay, choke means limited. Okay, so choke convergent nozzle. Okay, so for choke convergent nozzle, okay, normally the exit pressure is higher than the ambient pressure. Okay, the exit pressure is higher than the for choke convergent nozzle. We have the exit velocity will be equal to the speed of sound, A or C. Okay, the exit velocity will be equal to a speed of sound. So it is choke. Okay, and the exit pressure will be higher than the ambient pressure. Okay. So the pressure thrust depends on the difference between exit and ambient pressure. Okay, since that the exit pressure is higher, means it is not the same value as ambient pressure. So the pressure thrust exists. We cannot neglect it. Okay, so the pressure thrust, of course, depends on the difference of the exit PE minus PA in the thrust equation just now. Okay, because PE here is different than PA ambient. For choke convergent nozzle, okay, for choke nozzle, exit pressure is higher than the ambient pressure. Okay, and the second one, if we have the unchoked nozzle, this is more simplified, okay, or ideal case. Unchoked nozzle, when it is unchoked nozzle or unlimited air nozzle, means that jet velocities varies with the atmospheric pressure, okay. Means that we have exit pressure equals to ambient pressure. Okay, so this time for unchoked nozzle, we have exit pressure equals to ambient pressure. So the pressure thrust is negligible, zero. Okay, we assume it as zero. Okay, actually, this correlation, this definition about jet nozzle affecting the thrust, it relates with your knowledge. You have to flashback a bit. It's about the effect of Venturi. Okay, Venturi. Okay, you also will learn. Will do experiment on Venturi effect in lab thermofluid with me, right? Okay, so uh, by applying the effect of Venturi, I suppose you have learned the effect of Venturi in aerodynamic one. Okay, so the effect of Venturi, we know that when we Venturi is like a convergent divergent nozzle, right? Okay, first part is the convergent part until at the throat, okay, which is choke or unchoke, that at that point location, right? So normally in a Venturi or convergent nozzle, we will try to reduce the back pressure, right? We reduce the back pressure, okay, so that when we reduce the back pressure, the fluid or the air will be allowed to enter to flow in the Venturi, right? When the back pressure is decreased, okay. So the fluid flow, the air will flow into the Venturi or into the nozzle, okay. And as the fluid flow, the pressure is decreasing, kept decreasing. We manipulate the pressure, okay. We decrease the pressure, and at the same time, the velocity of the fluid is increasing, okay. This is through Venturi effect. Okay, and you can also see this through equation, the equation nozzle that we have revised in last 2 weeks. Okay, I show you the nozzle equation between area, pressure, velocity, nozzle, right? Okay, so that is the relation in terms of mathematic relation. But in physical, okay, in real, to understand that by using we learn that by using the Venturi effect, okay, or convergent nozzle effect. So when we pressure is decrease, and the fluid flow and velocity will increase. Okay, so this velocity will keep increasing. There is a maximum will increasing, means that and the fluid flow, the mass flow rate of the fluid will keep increasing as well in the convergent nozzle, right? when the pressure is decreasing, so we let the fluid flow in the venturi or in the convergent nozzle. So the mass flow rate will keep increasing as well. Velocity increasing. Pressure decrease, but velocity and mass flow rate increase. However, it is up to one point, which is at the throat. Okay? Or we call it choke point, throat point. We call it critical point. Okay? C, we know it as C, right? BC, VC, right? So, at this critical point, at the throat of the venturi, even though if we keep decrease keep lowering the pressure, the bed pressure at this throat point, at this location, the mass flow rate will not increase anymore. Okay? At first, in the convergent nozzle or in the venturi at the inlet, when we decrease lower the bed pressure, the mass flow rate will increase. So it flow inside the venturi, and the fluid velocity will also increase. But until up to some point, which is at the throat or at the critical point, okay, at the throat of the venturi or convergent divergent nozzle, this value of mass flow rate will not increase anymore, even though if we kept lowering the bed pressure. It is like a maximum, or we call it as limited. It is limited, okay? So it is choke, okay? So this is the point where we call the sonic point or critical point. Means that the Mach number is equal to 1. Means that at this point, at the critical point, the velocity of the fluid will be equal to the speed of sound, okay? Which is at the Mach number equals to 1. Okay, so it is choke, is already limited, okay? Even though if we lower the bed pressure. So that is what it means, okay? Okay, unless if we have unchoked nozzle, okay, the second one just now, unchoked nozzle means that the entire flow is subsonic. Okay, so that's why PE equals to PA. So the flow will the air will just flow in the nozzle, okay, without limiting condition. Okay, but for the first one, choke convergent nozzle, at first it will decrease, and then up to some point, okay, it will not increase anymore. The speed will not increase anymore. If we continue to have convergent nozzle, it will not increase anymore. So that's why we add the divergent nozzle. So that's why yang dia jadi convergent divergent nozzle. Because if we keep just use the convergent nozzle and we keep decreasing the area, the mass flow rate will and the velocity will not increase anymore. Okay, so that's why we need to add divergent nozzle, okay, to increase the velocity to a high speed gas. Okay, so that's why in the end we add the divergent nozzle. That's for choke. For unchoke, it is subsonic. Okay, so you will not be supersonic. Supersonic, convergent divergent nozzle. Okay, next, factors affecting thrust, airspeed. Okay, the airspeed, of course, airspeed, or sometimes we call it as flight speed. Okay, the U or U naught. Okay, so if the exit velocity UE is constant and U airspeed or flight speed is increasing, then we will have the net thrust, the thrust decrease. This can be seen through thrust equation just now. Okay, the thrust equation just now, you have this. So if mass flow rate ME here is constant, and then you have the VE is constant or UE is constant, and then you have the V, flight speed, increasing. Okay, so means that this net thrust will decrease, or you can see here also. Okay, so if this is constant, this is increasing, so net thrust will decrease. Is that right? Okay. Okay. Next one is so this one you can see by looking at the thrust equation, the simplified thrust equation. Okay. Next one is the mass airflow. Okay, this relates with density of the air. Okay, you can imagine this through this density of the air. Okay, depends on the ambient temperature and ambient pressure. Okay, we can determine the density of the air. Okay, if ambient temperature rise, okay, density will decrease and thrust will decrease. Okay, so how we see this? Okay, ambient temperature rise. You imagine you have water. So if the temperature of the water increase, means that a hot water. Okay, so the hotter, okay, the more hotter temperature, okay, will usually goes at above. Okay. Okay, at the bottom will be the more colder, okay, cold temperature. Okay, so if we keep increasing the temperature of a fluid, okay, it will rise. It will goes up. Okay, that is the normal phenomena. Okay, so so because normally the solid is which is have a high density is at the below. Okay, so gas which is normally hotter and low density, so it will be at the above. Okay, so that's why for density, if we increase the temperature, then density will decrease. Okay, it will go up, so density decrease, and at the same time the thrust will decrease. Okay. So next, if ambient pressure rise, how about if the tekanan pressure rise, then the density will increase. So for example, yes, if you look at the solid gas, right? So the solid have more pressure. Okay, so the ambient pressure rise. So the density will increase, more pressure inside, so more density, and the thrust will increase. Okay. Okay, so that's why uh, in a flight, okay, movement, okay, at the bottom here compared to the above in the sky, okay, so the temperature at below here in the earth is higher than the temperature up the sky, right? So that's why if we goes further, the thrust will increase further. Okay. And then next, the altitude. Okay, this is also linked. Okay, so this is also function of density. So if altitude is increased, okay, means that the ambient pressure will decrease. So when we are at the top, okay, when we are flying, okay, when we keep increasing our altitude, okay, when we're flying, so the ambient pressure will decrease. So that's why sometimes we have problem with our ears, because the initial ambient pressure that in our ear is different than the ambient pressure when we goes up flying. Okay, so the ambient pressure will decrease when we goes up, and the thrust will decrease. Okay. And then optimum altitude for long range cruising and nominal speed. Okay. Okay, so however, we have a nominal speed, a nominal maximum optimum altitude, which is around 11,000 meter for commercial aircraft. Okay, so after this height, the temperature will not rise anymore. Okay. Okay, so this is 11,000 or 10,000 meter is the optimum altitude for long range cruise to have a nominal speed. Okay, for cruising speed, we need around 11,000 meter. Okay, what else do I want to share with you? Okay, so that's why a lot of the commercial aircraft will try to fly at night rather than in the siang, okay, in the morning or in the afternoon. Okay, kebanyakan flight, lebih banyak yang long range. Okay, the long range flight will try to schedule flying at night rather than in the morning. Okay, because before this I study in France, so every year I go back Kuala Lumpur, France. So the flight usually to France or even to transit to Dubai usually will fly at night, right? 11 p.m., 2 a.m. Okay. So now I understand why my flight schedule is always like that, because at night the ambient the temperature is lower than in the morning or afternoon, siang. Okay, in the daylight. Okay, at night the temperature is lower. So when the temperature is lower, the thrust will increase. Okay, so that's why we choose to for long range flight, we choose to fly at the night. Okay, short range, okay, to minimize the fuel use, this to save fuel as well. Okay, so because at at night lower temperature, so the thrust will increase, the thrust will be better, thrust will be better, so we do not need too much fuel. Okay, so we can save a bit fuel, so that's why. Okay, next, other parameters is the, okay, but this is not usually used, okay, but just to let you know the definition. Okay, so just to link it with to link this propulsion part with other structure, material, aerodynamic parts of aircraft. Okay, when you want to design an aircraft, you have to consider also the aerodynamic, the structure, etc. Right? Okay, so that's why you not only learn propulsion. Okay. So, in a design objective, or there's a lot of things that we want to optimize, we want to minimize, of course. Okay. So, we have this brigade range equation. Range means the distance. Okay, to get a optimum distance, we can calculate it by using these parameters. Okay, so this mass flow. This is specific thrust. This is the length, okay, etc. Velocity. Okay, so this brigade equation involves not just propulsion part, but also the structure part, aerodynamic parts, etc. So here in our propulsion course, you only look at one part of the engineering of the aircraft space design. Only one part, which is the specific thrust or thrust here. So means that you also need to consider the structure, the materials, the aerodynamic, etc. Okay, to get an optimum design of an engine. Okay, so here in propulsion we only learn one part, which is here. The weight also, okay, so the weight with the structure, we also need to optimize the structure. Okay. Okay, so other parameters, other important parameters. Okay, so we have propulsive efficiency. Okay, so this is very important that we are going to use a lot of time, propulsive efficiency. Okay, so in power plant, gas turbine, to characterize the efficiency of a gas turbine, we use thermal efficiency, right? Okay, but here for aircraft engine, aircraft application, we use the term propulsive efficiency, not thermal efficiency. We still calculate thermal, but the more important part is the propulsive efficiency, because in aircraft engine, the more important parameter is the thrust force, propulsion, to propel. Okay, so that's why we calculate the propulsive efficiency instead. Okay, so but the definition is the same. So we have at the it's like the initial inlet, the thrust power plus the power wasted in the exhaust, the total, okay, sorry, not inlet, but the total over the thrust power that actually we can produce. We are able to produce, we are able to produce, okay? So we can also write this equation by this. So UT is the thrust power, means the thrust multiplied with velocity, you will get power in watt or joule per second. Okay, before this we have thrust in Newton. Okay, so thrust, that is Newton is thrust force. Okay, now we need to use the thrust power. So to convert it into power, we multiply it with velocity. And this is the power wasted in the exhaust. Okay, so assume there is a power wasted in the exhaust, which is linked with characterized by the mass flow of the exit. Okay, it's like the momentum, right? No, it's like a kinetic energy equation, right? 1/2 times mv square. Okay, it's just that v here is the wasted. Okay, so you have to do the difference between the exit and the initial. So this one, the difference is the wasted. Okay, so times with this, so you get the kinetic, okay, the power wasted. Okay, so this is the term, okay, like similar to the thrust equation, you have the simplified term, simplified equation of thrust. So for propulsive efficiency also, you have the simplified equation for propulsive efficiency, which is when we assume that the nozzle is unchoked, as I've mentioned just now, means that it is subsonic or it's ideal case, and the F, the fuel, is negligible. Means it's not null, it's not zero, it's just that it is very small compared to the air mass flow rate. So if we assume it as negligible, so we only have this simplified term of propulsive efficiency. Okay, some theory, propulsive efficiency, okay, is converted into useful energy to replace loss due to aerodynamic drag, gravity, and acceleration. So propulsive efficiency is actually, we calculate the energy contained, okay, in the propellant. Okay, so this energy is converted into useful energy. Okay, and then proportion of the mechanical energy actually used to propel the aircraft. Or you can also define it as the mechanical energy. Okay, that is actually used, that is really used. Okay, that's why we have to divide by the power wasted just now. Also depends upon the characteristic of the nozzle, almost completely determined by the engine design. So it depends on the engine design. Okay, ada parameters thermal efficiency. Okay, as I've mentioned just now, there's we still use thermal efficiency term, but not as important as the propulsive efficiency. Okay, so however, I will still give you the thermal efficiency equation is different for different types of engine. Okay, so these are, but the definition is the same. Okay, the ratio of the power imparted to engine airflow over the rate of energy supplied in the fuel. So in thermal efficiency, you need to take into consideration the thermal energy produced by the fuel. So that's why you need to take into consideration the heat of reaction. It's like the CP, specific heat, right? So here we introduce the value heat of reaction or fuel heating value. Okay, because it's a thermal, so you need to consider the heating value of the fuel in the combustion process. Okay, this is last slide. So last one, we have overall efficiency. So overall efficiency is the thermal efficiency multiplied with propulsive efficiency. So overall efficiency of the engine. Specific thrust just now. And then last one, this is very, very important, is the specific fuel consumption or the cost of aircraft trip. So we call it, we define it as TSFC, okay, thrust specific fuel consumption, or sometimes you just call it SFC, specific fuel consumption. So this is the ratio of the fuel mass flow rate over thrust. Means that for 1 Newton thrust or 1 kilonewton of thrust, how much fuel is needed? Okay, how much fuel is needed in order to produce 1 kilonewton thrust or 1 Newton thrust? Okay, for example, we need 10 kilogram per second of fuel in order to produce 1 thrust, Newton thrust. Okay, so that is the definition of specific fuel consumption. Means that we try to achieve a lower SFC, specific fuel consumption as possible. Means that if we have a lower SFC, means that we use less fuel. Okay, lower SFC means that less fuel. So we try to achieve that, okay, to save fuel, okay, in performance. Okay, it's opposite than the specific thrust just now. For specific thrust, we want the specific thrust to be as high as possible, so that thrust is with only minimum, okay, value of mass flow rate air, we can produce better trust, okay, higher trust. Okay, I think that's all. Okay, so it's longer. I thought it will be less than the chapter one, but it's longer due to my explanation just now about the inventory. So I'll see you guys next week, inshallah, for a tutorial, some example exercise. Okay, so we'll do exercise next week. Okay, so I hope you can look at this later on. Okay, this class. Okay, so I'll see you next week, inshallah. Okay, assalamualaikum and see you next week. Okay.